What does it mean when the ocean floor itself slips sideways in silence? How can a fault hidden thousands of meters beneath the Atlantic suddenly release energy equivalent to millions of tons of explosive force, and yet leave no visible scar on the surface? Why do some earthquakes tear the Earth apart vertically while others, like this one, slide past each other with surgical precision? And perhaps most importantly, what exactly failed beneath the northern mid-Atlantic on March 21st, 2026, when a magnitude 6.7 earthquake sent seismic waves racing through the oceanic crust? Far from coastlines and human observation, at coordinates roughly 23.886 degrees north and 45.841 degrees west, a segment of the Earth's outer shell abruptly gave way. The rupture occurred at a depth of roughly 13.5 kilometers, or about 8.4 miles beneath the sea floor, placing it near the lower boundary of the brittle portion of the oceanic lithosphere. This is the zone where rocks are still capable of breaking suddenly rather than deforming slowly, and it is precisely within this narrow mechanical window that large earthquakes are able to occur. The setting is critical. This event did not happen along a subduction zone where one plate dives beneath another, nor along a continental fault like those that cut across land masses. Instead, it occurred along the mid-Atlantic ridge, a massive underwater mountain chain that marks a divergent boundary where tectonic plates are moving apart. At first glance, this might suggest a simple pulling apart motion, a process typically associated with normal faulting and shallow seismicity. But the mid-Atlantic ridge is not a straight, uninterrupted line. It is segmented into discrete sections, offset laterally by transform faults that accommodate horizontal motion between misaligned ridge segments. The earthquake took place within one of these offsets, specifically within the system known as the Kane fracture zone. This is not a minor structural feature, it is one of the most prominent transform systems in the North Atlantic, displacing the ridge axis by roughly 150 to 160 kilometers, or about 93 to 100 miles. This offset creates a fundamental mechanical problem. As plates move apart at the ridge, the segments do not align perfectly, forcing adjacent blocks of crust to slide past each other horizontally along the transform fault. Over time, this lateral motion is not smooth. Friction along the fault locks sections of the boundary, preventing continuous movement. Stress accumulates gradually as the surrounding plates continue to move. This stored energy builds silently within the rocks, increasing the shear stress along the fault plane. Eventually, the stress exceeds the strength of the locked segment, and failure occurs. When it does, it happens abruptly. The moment tensor solution for this earthquake provides a precise window into that failure. With a magnitude of approximately 6.64 on the moment magnitude scale and a double couple component of 98%, the signal is overwhelmingly dominated by shear motion. This is a key diagnostic feature. A double couple solution indicates that the energy release is almost entirely due to slip along a fault plane, with negligible contribution from volumetric changes such as expansion or contraction. In practical terms, this means the earthquake was purely tectonic in origin. The geometry of the faulting further reinforces this interpretation. The rake angles measured at approximately -6 degrees and -163 degrees indicate nearly horizontal motion. The dip angles at roughly 73 degrees and 85 degrees suggest that the fault planes are steeply inclined, approaching vertical orientation. Taken together, these parameters define a classic strike-slip mechanism, where blocks of crust move laterally past each other along near vertical planes. This is a crucial distinction. Along the ridge axis itself, earthquakes are typically driven by extension, producing normal faults where one block drops relative to another. Those events are usually shallow, often occurring within the upper 10 kilometers or about 6 miles of the crust. In contrast, this earthquake occurred deeper at 13.5 kilometers, aligning with the depth range expected for transform fault seismicity, which can extend down to about 15 kilometers or roughly 9 miles. Depth, in this context, acts as a fingerprint. It tells us not just where the earthquake happened, but what kind of tectonic environment produced it. The deeper occurrence indicates that the rupture penetrated close to the base of the brittle lithosphere, where temperatures and pressures begin to inhibit sudden failure. This suggests a relatively strong and well-developed fault capable of sustaining significant stress before breaking. The actual rupture process can be visualized as a sudden release of accumulated shear strain along a locked segment of the transform fault. For years, possibly decades, the plates on either side of the Kane fracture zone were attempting to move past each other. The motion was resisted by friction, causing elastic deformation in the surrounding rock. When the fault finally slipped, that stored elastic energy was released as seismic waves, propagating outward through the Earth. Based on the seismic moment, estimated at approximately 1.15 times 10 to the 19th Newton meters, and a half duration of about 4.5 seconds, the rupture likely extended over a length of roughly 40 to 70 kilometers, or about 25 to 43 miles. The amount of slip along the fault is estimated to be on the order of 1 to 2 meters, or about 3 to 6.5 feet. This is not a trivial displacement. It represents a significant reorganization of stress along that segment of the plate boundary. However, it is important to understand what this rupture did not do. It did not break the entire transform fault. Large fracture zones like the Kane system are composed of multiple segments, each capable of rupturing independently. The observed rupture length indicates that only a portion of the fault failed during this event. This segment-by-segment behavior is characteristic of oceanic transform faults and is consistent with observations from similar systems around the world. Comparisons with other mid-Atlantic transform faults, such as the Chain transform and the Atlantis transform, reveal a consistent pattern. These systems regularly produce earthquakes in the magnitude 5 to 6 range, with occasional events reaching magnitude 6.5 to 7. The depth distribution, fault geometry, and rupture characteristics observed in this event align closely with those global analogues. There is nothing anomalous about the behavior of the Kane fracture zone in this context. It is operating exactly as expected for a mature oceanic transform system. One of the more critical aspects of this earthquake is the absence of any significant magmatic contribution. At mid-ocean ridges, magma plays a central role in crust formation, and in some cases, it can influence seismic activity. Magma movement can produce earthquakes through the injection of molten material into cracks, creating complex signals that include both shear and volumetric components. However, in this case, the data shows no such influence. The 98% double couple component indicates a nearly pure shear mechanism, with no evidence of volumetric expansion or contraction. There are no signs of inflation, no hybrid signals, and no deviation from the expected strike-slip pattern. This effectively rules out magma as a driving factor. The earthquake was entirely the result of mechanical stress accumulation and release along the fault. The consequences of the rupture extend beyond the immediate release of energy. Earthquakes do not simply eliminate stress, they redistribute it. When a segment of a fault slips, it reduces stress in the area that ruptured, but increases stress at the edges of that segment. This creates zones of heightened stress concentration, which can in turn influence future seismic activity. Along the Kane fracture zone, the most immediate effect is an increased likelihood of aftershocks. These are smaller earthquakes that occur as the crust adjusts to the new stress distribution. In some cases, these aftershocks can reach magnitudes of 5 to 6, representing significant events in their own right. Additionally, the increased stress at the boundaries of the rupture may load adjacent segments of the fault, bringing them closer to failure. There is also the possibility of stress transfer to neighboring transform faults. While the interaction between separate fracture zones is generally weaker than within a single fault system, the redistribution of stress can still have measurable effects. Nearby faults may experience slight increases in stress, potentially influencing their seismic behavior over time. In contrast, the interaction between this transform fault event and the ridge axis itself is limited. The ridge operates under a different stress regime, dominated by extension rather than shear. As a result, the coupling between these systems is relatively weak. The earthquake is unlikely to have a significant direct impact on ridge axis processes or to trigger normal faulting events in that environment. At larger scales, there is no mechanism for this earthquake to trigger distant seismic events. The absence of nearby subduction zones and the localized nature of the stress changes mean that the effects are confined to the immediate region. This is a key point in understanding the broader implications of the event. Despite its magnitude, it does not represent a cascading failure or a precursor to a larger, system-wide rupture. Taken together, all lines of evidence converge on a clear interpretation. This was a large strike-slip earthquake occurring along a well-defined transform fault within the Mid-Atlantic Ridge System. It involved the sudden lateral movement of crustal blocks along a near-vertical fault plane, driven by the ongoing motion of tectonic plates. The depth, mechanism and rupture characteristics all align with established models of oceanic transform fault behavior. In essence, this earthquake represents a textbook example of how the Earth accommodates the complex geometry of plate boundaries beneath the ocean. It is a reminder that even in regions defined by divergence, where plates are moving apart, the mechanics of that motion can produce powerful lateral forces. These forces, when resisted and then suddenly released, generate earthquakes that are both precise in their mechanics and significant in their energy release. And yet, for all its power, the event remains confined to its structural context. It is not an anomaly, not a deviation from expected behavior, but rather a clear expression of the underlying tectonic framework. The Mid-Atlantic Ridge continues to evolve, segment by segment, fault by fault, with each earthquake marking a momentary adjustment in a system that has been in motion for millions of years. The March 21st event is one such adjustment, a brief but powerful release of accumulated strain along the Cane fracture zone. It does not signal instability in the broader system, nor does it indicate any unusual or unexpected process. Instead, it confirms that the mechanics of plate motion, even in the most remote parts of the ocean, are consistent, predictable, and governed by the same physical principles that shape the Earth's surface everywhere. What happens after the rupture is often more revealing than the rupture itself. Once the fault has slipped and the primary shock has passed, the surrounding crust does not simply settle into a new static state. Instead, it enters a period of mechanical adjustment, where the redistribution of stress begins to dictate the next sequence of events beneath the ocean floor. In the case of the March 21st magnitude 6.7 earthquake along the Cane fracture zone, this post-rupture phase is governed almost entirely by how shear stress was shifted along and around the failed segment. When a locked portion of a transform fault suddenly gives way, it relieves stress within the rupture zone but transfers additional stress toward its edges. This creates a pattern where the central section becomes temporarily more stable, while adjacent segments are pushed closer to their own failure thresholds. This is not a random process. It follows well-understood mechanical principles tied to how elastic strain is stored and released in brittle rock. Immediately following the main rupture, the most likely outcome is a sequence of aftershocks distributed along the margins of the slipped segment. These are not independent events, but are directly linked to the stress changes imposed by the main shock. Their depths typically mirror that of the original rupture, clustering within the same 13 to 15 kilometer range, or about 8 to 9 miles beneath the seafloor. This reflects the fact that the brittle portion of the lithosphere remains the active zone for failure. while deeper regions behave more ductilely and do not fracture in the same way. The size distribution of these aftershocks tends to follow a predictable decay pattern. Smaller events occur more frequently, while larger aftershocks become increasingly rare. However, in a system like the Kane fracture zone, it's entirely plausible for follow-up earthquakes to reach magnitudes in the 5 to 6 range. These would represent continued adjustment along the same structural system, rather than the activation of a new or unrelated fault. Beyond the immediate aftershock zone, the redistribution of stress can influence neighboring segments of the transformed fault. Because the Kane system is composed of multiple discrete sections, rather than a single continuous fault plane, each segment responds independently to changes in stress. If one segment experiences an increase in shear stress due to the recent rupture, it may move closer to failure, effectively shortening the time until its next earthquake. This process is often described as stress loading, and it plays a central role in how seismic activity migrates along transform systems over time. This segmented behavior explains why large oceanic transform faults rarely rupture in their entirety during a single event. Instead, they break in sections, each earthquake releasing stress locally while redistributing it regionally. Over long timescales, this creates a pattern of sequential ruptures that propagate along the fault system, but never as a single, continuous break. The March 21st event fits cleanly within this framework, representing the failure of one segment within a larger, interconnected structure. An important factor in understanding the limits of this process is the mechanical contrast between transformed faults and the adjacent ridge axis. While both are part of the same plate boundary system, they operate under fundamentally different stress regimes. The ridge axis is dominated by extension, where plates are being pulled apart, leading to normal faulting and shallow seismicity. In contrast, the transform fault accommodates horizontal motion, producing strike-slip earthquakes at greater depths. Because of this difference, the coupling between these two environments is relatively weak. The stress changes generated by a strike-slip earthquake along the transform fault do not efficiently translate into the extensional regime of the ridge axis. As a result, the likelihood of this event triggering significant seismic activity along the ridge itself is low. The mechanical conditions simply do not favor direct interaction between these distinct modes of deformation. At the same time, the broader lithospheric structure imposes limits on how deep and how large these earthquakes can become. The oceanic lithosphere at this location is relatively young and warm compared to continental regions, which means the brittle zone is thinner. This constrains the maximum depth of seismic rupture to around 15 kilometers or roughly 9 miles. Below this depth, temperatures are high enough that rocks deform plastically rather than fracturing, effectively preventing deeper earthquakes. This thermal structure also influences the size of the rupture. Because the brittle zone is limited in thickness, the vertical extent of the fault plane is constrained. This, in turn, limits the total area over which slip can occur, placing an upper bound on the magnitude of earthquakes in this setting. Events in the magnitude 6.5 to 7 range represent the upper end of what is typically observed for oceanic transform faults, and the March 21st earthquake falls squarely within this range. Another aspect worth examining is the role of friction along the fault interface. The behavior of a transform fault is heavily influenced by the properties of the materials along the fault plane, including factors such as roughness, composition, and the presence of fluids. In general, oceanic transform faults are thought to have relatively high frictional strength, which allows them to accumulate significant stress before failing. This contributes to the occurrence of larger, less frequent earthquakes, as opposed to continuous low-level slip. The abrupt nature of the rupture suggests that the segment of the Kane fracture zone involved in this event was strongly locked prior to failure. Over time, shear stress built up as the surrounding plates continued their motion. When the fault finally slipped, it did so rapidly, releasing that accumulated energy in a matter of seconds. The estimated slip of 1 to 2 meters, or about 3 to 6.5 feet, is consistent with this type of stick-slip behavior, where long periods of stress accumulation are followed by sudden displacement. From a wave propagation perspective, the energy released by the earthquake traveled outward in all directions, moving through the oceanic crust and into the underlying mantle. These seismic waves would have been detected by instruments across the globe, providing the data needed to reconstruct the event's characteristics. The relatively short duration of the rupture, on the order of a few seconds, indicates that the faulting process was efficient and localized, without prolonged or complex breaking. Importantly, the absence of any significant volumetric component in the seismic signal confirms that there was no meaningful contribution from processes such as fluid injection or magma movement. This reinforces the interpretation of a purely mechanical origin, driven entirely by tectonic forces. In environments where magma plays a role, the seismic signature often becomes more complex, reflecting a combination of shear and volumetric changes. That complexity is not present here. Looking at the system as a whole, the earthquake represents a momentary adjustment within a continuously evolving plate boundary. The mid-Atlantic ridge is not static. It is a dynamic system where new crust is constantly being formed, and existing crust is being reconfigured through processes like transform faulting. Each earthquake contributes to this ongoing evolution, incrementally reshaping the geometry of the plate boundary. The Kane fracture zone, with its significant lateral offset and well-defined structure, serves as a key component in accommodating the mismatch between ridge segments. Without these transform faults, the plates would not be able to move apart efficiently. Instead, stress would build to levels that could not be sustained, leading to more widespread and potentially more chaotic deformation. In this sense, the earthquake is not just a release of stress, but a necessary function of the system, allowing it to continue operating within its mechanical limits. Over longer timescales, the cumulative effect of these earthquakes is the gradual lateral displacement of the oceanic crust along the transform fault. Each event contributes a small increment of motion, adding up over millions of years to produce the large offsets observed today. The 1 to 2 meters of slip associated with this earthquake may seem modest in isolation, but it is part of a much larger pattern of movement that defines the structure of the mid-Atlantic ridge. There is also an important implication in terms of predictability. While it is not possible to determine the exact timing of individual earthquakes, the behavior of transform faults follows consistent patterns that allow for probabilistic assessments. The occurrence of a magnitude 6.7 event indicates that the fault is active and capable of generating significant earthquakes. The redistribution of stress suggests that adjacent segments may now be closer to failure, although the timing of any subsequent events remains uncertain. What can be said with confidence is that the system will continue to produce earthquakes as long as plate motion persists. The forces driving this motion operate on a global scale, powered by processes deep within the Earth's mantle. These forces are steady and continuous, ensuring that stress will continue to accumulate along plate boundaries, including the transform faults of the mid-Atlantic ridge. In the end, the March 21st earthquake is not an isolated anomaly, but a clear expression of these broader tectonic processes. It reflects the fundamental mechanics of how the Earth's outer shell accommodates motion, even in regions far removed from human observation. The lateral slip along the Kane fracture zone, the depth of the rupture, the absence of magmatic influence, and the pattern of stress redistribution all point to a system functioning exactly as expected. There is a certain precision to it. The fault was loaded, it failed, and in doing so, it transferred stress in a way that sets the stage for future events. Nothing about the process is random, even if the exact timing appears unpredictable. It is governed by physical laws that apply uniformly across the planet, from the deepest ocean basins to the highest mountain ranges. And beneath the surface of the Atlantic, the process continues. The plates keep moving, the faults keep locking and slipping, and the cycle of stress accumulation and release carries on without pause. The magnitude 6.7 earthquake is just one moment in that ongoing sequence, a brief but powerful reminder of the forces shaping the Earth from below. If you want more deep, technical breakdowns of seismic events like this, clear, precise, and grounded in real geological processes, make sure to like, share, and subscribe, and tap that hype icon to help this reach a wider audience.